begin whenever you're ready.
Okay, thanks. So I'm going to be presenting a limited case for reification by type inference. And the assumption that I have is that my audience, all of you, will know what reification is, that it's for doing reflective reasoning and operating on a structured representation of something. And the goal with this is to perform some operation that requires a structured representation. And I've presented in the past other methods of doing reification, and there are a number of methods of reification that are fairly well known. And what I want to present here is a cute trick that I discovered in the process of solving a puzzle for getting just type inference to do reification for you. And my hope is that you will understand how this trick works and how to do this reification by type inference. And then maybe in the future, if you discover some area in something that you're working on that requires this sort of reification, or where this is applicable, you can use this trick and maybe even extend it. And because the goal of this is to have you all understand this trick pretty deeply, I want to welcome questions about it throughout the presentation. Okay, so the particular example that I'm describing is to perform some operation which requires a structured representation of curried types. In this particular case, the example is reversal. And this will be done with the help of some notation. So the ultimate goal of this example is to have some operation on structured types, for example, reverse uncurrying, that with a notation on some sort of expression will allow you to reverse the curry structure of the types, of the arguments. And this is without using any sort of Ltac, just using type inference. And I want to note that it's possible to do currying already just with the notation system, and I'll be displaying the implementation of this shortly. And the real trick is how to get the structured representation so that you can write uncurrying on that structured, reversal of the structure on the structured representation. So now let me move to the implementation of a normal currying notation. And here we can define a function that takes a curried function and turns it into an uncurried function. And we can see that this gives the correct type, for example, on add, and that if we unfold it, it gives the correct function, the correct uncurried addition function. The problem with this uncurrying is that it only does the first two arguments. It doesn't uncurry any more than that. And you could define a notation, for example, uncurry3 here, that will then let you uncurry 3 arguments at a time. And here you can see the function with 3 arguments uncurried. And in fact, you can define a generalization of this that works with any number of arguments. And what this generalization does is basically you use this special ... for recursive notations, and you say that before every function binder, you insert a call to uncurrying. And the downside of this, as far as I can find, is that your final binder needs to have the same form as all of the others, and so we need to add this extra dummy unit binder over here. But if you're willing to have sort of the end of your arguments pick up an extra unit, then you can in fact define this uncurry notation that handles an arbitrary number of arguments and uncurries the function that you write down. Let me pause for a moment and ask if there are any questions on defining this notation so far. I'm about to move into the structure of the actual reification by type inference.
Could you just quickly remind me of the semantics of CBV bracket uncurry2 bracket?
Yes. So CBV is call by value. It's a reduction strategy, and it takes, if you want to, you can pass it a whitelist of definitions of names to unfold. And so this means unfold uncurry2 in this term, and also perform beta, iota, and zeta reduction.
Okay,
Any
so I
other
guess
questions?
the minus quote plus quote up there, then that's a blacklist or something like
Yes, the minus, this is a blacklist, and it automatically looks up the constant associated with the notation plus in the current scope.
Okay, cool.
Cool. So for reified currying, we need a inductive type to describe the structured representation of our types. So here I've made this inductive uncurry types. That's basically just a linked list of types. And we need a denotation function to turn this back into a type. And we can see that, in fact, this gives us the right sort of structure with an extra unit at the end. If we have nat and then bool and then set, this gives us, this gives us nat cross bool cross set with an extra unit at the end. And now here's the real driver for doing the reification here, is that our uncurry function as its second argument takes the denotation function applied to the list. And so again, we take a function that has two arguments in curried style and turn it into one that takes one argument in the uncurried style. And the trick is that here, this will be all of the remainder of the arguments already uncurried. And then we build the same notation as we did before, except the function that we put before each binder is this uncurrying function. And there's one more thing that we need to change. If we just do it leaving unit at the end, we get a type error, which is that you can't unify unit with denote uncurried of something. And this is actually sort of indicative of where the reification gets started, because essentially what you want to do in reification is you want to invert the denotation function. You want to figure out what expression leads to the given denotation. And so if we replace unit with the denotation function applied to the tail of our list, and then we do the same thing, we see that this time it works, and it builds the entire list of reified type structure for us. And the way that it does that is that at every function node, we call this uncurry function. And the uncurry function tells us how to take a step in reification. It says that to go from something arrow denote uncurried of what we have so far to take another step in reification, we can cons those two types together and have a denote uncurried there. And that gives us the function that we want. And now as an example that I'm not going to describe all the details of, because this is unrelated to the actual reification process, you can define a function on the structured representation of types that reverses the uncurrying structure. And when you do that, you get this large, nasty expression. But if you take a little bit more care and you remove the unit at the end as well, define everything in continuation passing style, you can get this function that you've applied to the reification notation that gives you, in fact, the uncurried, the reversed uncurried function. And that is my limited case for reification by type inference with this one application. I will now take any other questions that people have. Thank you.
Thanks, Jason. Are there any questions?
May I?
Yes, of course. Go on.
Hi, Jason. Thank you for your talk. I have a question. You define a type called unquery types, which is a list of types. Can't you use standard lists?
I could use standard lists. I've gotten the habit of not using standard lists because it's very easy to get universe inconsistencies if you put types in a list from the standard library. In particular, if you want to put, I think if there are some list types or some types involving lists that if you try to put them inside lists from the standard library, then you get, you can get universe inconsistencies.
Okay, I see. If I may ask another question,
Sure.
Do you have other examples in mind where you can use your technique?
So the particular example that led to me doing this was that someone asked me how to get a particular notation for, what was it? It was for COMSERT's notations for her logic. And I was like, oh, there's a cute trick that can be used here. I think I've also seen something like this used in notation for telescopes in, I think it was either Iris or StudPP. I think Tej pointed me at this. But I don't, in fact, have more applications in mind. And my hope with this is that someone in the audience will see it as a cute trick, and then later on, when they have a need for it, they'll be like, oh, I know how to do something like this. That's how the applications will grow.
Okay, thank you.
I wrote that telescope code in StudPP. I don't know this trick, but it might be that I'm using it without realizing what I'm doing.
I think there's a place where I think the notation for lambdas in the telescope, in order to get the lambdas to actually live in the telescope type and to be able to be modular with other operations on telescopes. I think there's a trick that's very similar to this that gets used.
I mean, we are certainly stretching type inference. In fact, I think it was partly due to this that the Coq developers added this new, there's a new hint you can give about in which order type inference like acts on functions with dependent types.
Oh, the bidirectional type checking hints?
Yes, exactly. I think that was partially a reaction to issues we had with the telescope thing when we talked with the Coq devs. So I mean, certainly we are doing something like we are stressing type inference in ways. So yeah, I mean it's possible that we're doing something like that here, there in the telescope things. I would have to look at it again, but it's hard. It's really hard to see these patterns for me anyway. I wouldn't know how I would say it's the same thing.
Okay.
I wanted to ask you to also explain the CPS stuff a bit more, but I guess we don't have time anymore. So, well, shame.
You can always discuss offline, but now it's time to move to the next talk. Thanks again, Jason.
Yeah, thank you.